This one again.
F10.
Possible.
Yes. You understand?
I want to sleep.
Sleep forever. Yes.
Not forever.
Not forever. Just this week.
Yes.
All right. We'll continue. Oh no, what?
W O no.
Huh?
First graph of UN.
That's fine. Yeah. Something like this. Sit down.
Yeah. Okay.
Great. Right. We'll continue now. Oh no, please, please, I must continue. I thought Sylvie said don't do anything for the rest of the month.
Yeah.
I don't believe her.
No, no, I just want to ask question.
Oh, okay. Right, next lesson, please. Please write the title down. Thank you.
Long title.
Let me open that up neatly. Right, there you go. Do you remember the mechanics lessons about the three forces?
No.
No.
Which one?
The three force theorem. You remember it?
What three force?
Yeah, I see. I've forgotten it. Do you remember this mechanics lesson? The three forces? Three force theorem?
What's the title?
Three force theorem. You remember it?
No.
I'm doing revision with the September students
September.
and they have forgotten it.
Yeah.
Yeah. And I said, guys,
Long time ago. No.
you remember this one, the three forces, and you have one force,
Oh.
and one force, yeah? So I was doing an exam question with them, and I had this drawn, and there was one force, and one force. And I said, what type of this problem is this? I said, no.
No.
So yes, make sure you do revision because you will forget things.
Okay.
Just look at those September students. Right, okay. Right, so far I've been using the word voltage, but really we don't always say voltage. We call it potential difference, is what I should really say for voltage. Potential difference is just another name for voltage. Potential difference is more common nowadays, or at least it's just maybe more common. I like voltage, but I should maybe really say potential difference more often. So if you hear me say PD, potential difference, I mean voltage. PD for short. Means voltage. Yep. Got that? Yep. Now, another word. Electromotive force, also called EMF. So let's use our English skills when you're ready. Yep. So electromotive force. Let's break it up into three parts. EMF. EMF, electromotive force. Electro. What could that mean? Electricity. Whoops. Motive, motion, and force, force. So it's something like electrical motion force. So what could that be? Any ideas?
Electrical motion, kinetic energy.
No.
Oh, the charge moving.
Yeah, we're getting closer. So when you have a charge moving and it can do work, something must be pushing it.
Oh, potential difference.
It's related to this, yeah. In other words, EMF is the voltage from a battery. Yeah? So if you have a battery and it can do work, like you put your battery into your toy and the toy does work, the battery develops, it has an EMF. In fact, sorry, the definition is very long. I want, before you write the definition down, I want you to, no, don't write it just yet. I want you to try and understand it before you write it down. So if I have like the battery on my phone, so this battery, it can do work. You know, I can use my phone, I can make a call. So there's a voltage here. Okay? So there's like a force inside here that's doing work, you know. If the voltage here is 12 volts, well it's not 12 volts, this here is 3.7 volts. We say this battery has an EMF of 3.7 volts. So it's the same. So it's like another word for the voltage of the battery. Okay? So this battery here, EMF 3.7 volts, it means it can do 3.7 joules per coulomb of work. There's like a little force here that's doing this work. So the definition is very boring and long and technical, but basically that's what it means. Now, unfortunately, this definition is sometimes on the exam. So you might just want to accept that you won't be able to remember this definition because it'll be like 1 or 2 marks. It's much more important that you can get 18 out of 20. I'm fine if you lose 2 out of 20 because you don't remember this, okay? Because that's life. You need to be practical. So if you can do the rest of the question, get 18 out of 20, perfect. If you only lose 2 marks or 1 mark because you don't quite remember this definition, and I don't expect you to remember this definition, I wouldn't even expect a native speaker to remember this definition, that's okay. But you can at least write it down and pretend you can remember it. Yeah. This is the longest definition you could have in the exam. I know. Got it?
Yeah.
So, what is the difference between EMF and potential difference? So, for example, an EMF of 1 volt means each coulomb of charge is given 1 joule of energy, whereas a potential difference of 1 volt between 2 points means each coulomb could do 1 joule of work. So you're like, huh? What's the difference? So let me draw the difference, okay? So here, so if this has, oh, come on, don't break. Oops, that's not it. Come back. Come on. Come on, you can do it. Yes, we're back. Okay. So here, if I say the EMF equals 1 volt, what that means is your 1 coulomb of charge is given the ability to do 1 joule of work. So here's our coulomb. Here. I can do 1 joule of work. Because the EMF is 1 volt. It means it gives it the ability to do 1 joule of work per coulomb. Then here, the coulomb travels through the resistor, and if the voltage here, potential difference is 1 volt, what that means is it did 1 joule of work. It lost its ability to do more work. It already did it in the resistor. Maybe the resistor is a light and some light came off, whatever. So basically, you can think about the difference like this. EMF is measured in volts and it gives, whereas potential difference is measured in volts and it's done. So EMF of 1 volt means you're given something the ability to do 1 joule of work per 1 coulomb, and then a potential difference of 1 volt means that energy has been converted, it's been spent, it's changed into heat or whatever.
What is
This?
yeah.
Do you get the difference between EMF and PD?
Explain again.
So EMF of 1 volt means my 1 coulomb was given the ability to do 1 joule of work. So it has 1 joule inside of it. A potential difference of 1 volt means this 1 coulomb did 1 joule of work. It no longer has the ability to do this work. It has spent its energy. Oh my goodness. Alright, okay. So, an EMF of 1 volt gives 1 coulomb the ability to do 1 joule of work. You know you can get this on the video later when you watch it again, right? So one more time, the EMF of 1 volt gives the 1 coulomb the ability to do 1 joule of work. But a PD of 1 volt, yeah, the PD of 1 volt means the coulomb, or the 1 coulomb did 1 joule of work. So the units are the same. You measure both of them in volts. So I think this is the reason why people don't like the word voltage. Because when you say EMF and PD, you can make it clear. So EMF is given, PD is taken. Whereas voltage you can use to describe both. Yeah? Okay, continue. No? Yes? These are just little doodles. Yes? Okay. So this is actually a very important circuit for this lesson. And I'll explain it. No, you know what? I'll draw it again, okay? So this is what I want to draw. I'll draw something like this. So, what you have is a battery, like an AA battery for your toys. And then connected to the battery then is some resistor. Usually a resistor you can change, yeah. So resistor here. And then there's an ammeter here. And then connects back up here. And then we connect a voltmeter here around the AA battery. Now, when we think about a battery, we think about it being like inside there's a few cells, something like this. And that's true. Inside of it there is a few cells, but also inside of a battery there's a small resistor. Now there isn't really a small resistor. We're imagining it is like this. That in some way there is a perfect part, and then there's a part we don't want. Because, you know, when you take your, like on your phone, when you take out well maybe not this phone, maybe your phone, this battery gets a little warm. Now you don't want it to get warm. Why not? It's wasted. It's wasted energy. And the reason it gets warm is it's like there's a small resistor inside it. Now, of course, it's not really a small resistor, because if there was, then you should take it out. But this is what I mean when I say it's like a small resistor inside of it. Okay? So what we want to find out is how big the small resistor R is. Okay, so you can draw this, please. Oh, and please notice, look, please note, sorry, this one is negative, I should do it this way. You can draw the voltmeter up here, or you can move this down to here and move this down to here and draw the voltmeter here. Will it be the same? Yes, because look, there's nothing here and there's nothing here. There's nothing happening here. You know, if you put this up the top, it's the same as being down the bottom. Like this. No difference. Okay, so draw this. And by the way, I'll just give you a little bit of vocabulary. These parts of the batteries, the top and the bottom, does anyone know the name of the top or the bottom of the battery? Ah, yeah, but the name for both of them. Good guess, but no. There we go. Terminals. Okay, so in our mind, we have some EMF here. And I don't like drawing my voltmeter on the top. I like drawing my voltmeter down the bottom. Because in my brain, it makes more sense because I'm looking at the voltage through this. So I should put the voltmeter around it. You understand? No? What do you need? Just 1 second, man, to look up. If I put the voltmeter here, do I get the same number as if I put the voltmeter here? Yeah. And what about if I put it here? Yeah. And if I put it here? Yeah. And if I put it here? Yeah. So what I'm saying is putting the voltmeter on the top is exactly the same as having the voltmeter on the bottom. But I like it on the bottom, so I'm going to draw it here. Okay. And then we have EMF, I'll call it E here. Right, let's use Kirchhoff's loop rule. So I start with, hang on, I. Okay, I start with E. What's next? Start here, go to the right. E minus I or, and let's call this or here, minus I or equals 0.
Yeah, smaller r is a small in this, right?
Yeah, that's a small or and that's a big or. Now, the way this experiment works is that you can, of course, know the I because you can see it here, and of course you can know the V. So what do you not know?
The r,
You don't know this. What else?
that bigger r.
You don't know this, and you don't know this. So I want to replace this here, replace it. If I use my triangle, I can say or equals V over I. So you can say E minus I or minus V equals 0. And I can rearrange this a little bit. I can say I or equals E minus V. Sorry, I or equals minus V minus, let me get my signs right. I'm taking this over. E minus V plus E. Okay, so I have I or equals minus V plus E. Then I can say or, sorry, I equals minus 1 over or V plus E over or.
I think it's wrong.
No? I divided everything by or, yeah?
Yeah, and
No?
minus the positive I changed to minus also, right?
Huh? You think this is wrong?
No.
This is wrong.
Why don't you put the negative? Isn't it just divide r?
Yeah.
Yeah, but then if there's a negative at the front there, doesn't the plus after the v also have to be negative?
No, it's in brackets here. Huh? No, this is right. Trust me. Isn't it?
Like,
Right? Yes?
try to times it, see if it's
No, but the
equal.
minus just hits this.
Oh, alright.
Yeah.
My
Okay.
bad.
Now, if you look back here, um, V over 4 is, yeah, okay. Now I'm just trying to see what I'm trying to get to. I forget. Uh, Actually, oh yeah, I'm doing the, I'm writing the proof out. So yes, let me see. I'd like to usually have the voltage. Yeah, now this is something I always find very strange. I always feel like because you're changing the V, you should have the I on the y-axis. But often for these, I actually did this the wrong way around. I'm sorry. I shouldn't be trying to get the I should be trying to get the V. So if you can write this underneath, you can say V equals E minus I or. Then I divide. Oh no, that's it. I'm finished. Sorry. So now I have V equals minus or I plus E.
Beautiful.
No, I'm trying to get to a formula. I'm trying to get to this formula.
Okay.
Now I've got it, so I'm happy. Now, in the exam, sometimes you need to use, in the exam, I think they've done both versions. It should really be this one, I think, according to the syllabus, but the other one I gave you, it's not that it's wrong, but just forget about it. So, this is the one that really should be. So we put voltage on the Y and the current on the X. Because this is like Y, this is like X. So this one here is like M, and this one here is like C. So if you made a graph like this, where you have I here from the ammeter, and you had V here from the voltmeter, the graph will go down like this. So you could have a graph of some points, and then you can draw a line, and what will the slope here equal? Minus R. So you can get the result that R equals minus the slope. And what would the E equal? What's the E? Yeah, what's this called? This is called the intercept. So these are the results I want. I want you to make note of this, 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 and the graph. And you get the V from the voltmeter, and you get the I from the ammeter. So you can use this graph to calculate the internal resistance. That's what the R is called. R is called the internal resistance. Internal. You know this word? You should know this word. What's the opposite of internal? External, yeah. Grace, do you know this word internal?
Maybe.
What do you think it means? Which means? Inside. Okay. Continue.
No.
I see, because you were playing on your phone.
Not my phone, my computer.
That's worse. Okay, continue. I know we nearly finished. So look, there's only one question and then there's one homework question. And there's no surprise here. What do you think I ask you to do in the question is to make the graph. So, here is the potential difference and here is the current. So I ask you to make the graph and then use the graph to get the internal resistance of the cell and then to get the EMF of the cell. So when you draw the graph, you need to know the slope and the intercept. So all I need you to do right now is just write down this table. We'll make the graph and then we'll finish, okay? So just write down this table. Potential difference and current. Just the table, please. Yeah? No?
one is just protocol.
Oh no, 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 no. There's a new graph for you to make. Okay, can I draw this one?
No.
Grace and Sohi, do you have the numbers?
Yes.
Well, you can write them down, Amanda, when I'm typing them. Okay, so the first one is current, and then potential difference. Okay, so what's the current? Starts with
1.
1,
0.0, 0.9, 0.9,
0 point, it decreases by point,
point
I
1.
easy.
the current decreases by point 1, yes?
Yes.
Okay, and what about the voltage?
Increases by point 1.
Starting at
1.0.
and increases by point 1. Are you sure this is the right way around?
Yes.
Okay, and what's the maximum voltage?
1.9.
Okay. Right, so we'll make the graph. I put the current on the X and the voltage on the Y. Okay, we need scatter, we need this, and we need this, and we need this, and we need this, and we don't need this. And it's voltage, no sorry, V against I in amps, potential difference in volts. So notice the graph is going down like we talked. I will use Excel to make my line because I'm lazy and out of time. So here is the equation of the line. So what is the internal resistance here? If you look at the equation of the line. So what's the internal resistance? The small r is 1. 1 ohm. 1 ohm. No, no, but remember it's
Going
equal to
down.
Minus.
minus 1. R equals minus 1. So the R equals 1. And what's the EMF? 2.
The Y
Yeah.
intercept, which is 2.
2. Now look, if you do the graph the wrong way, for example, if you put voltage here, like I was doing at the start, voltage here and current here, it's not a big deal. The R would be 1 over the slope. So if your graph is backwards, it's not the end of the world. And in fact, that's what I was trying to say earlier, that in the past exam questions, I've seen them do the graph this way and the other way, which is wrong because they should only do it one way. So I think they want it this way really, where you put the I here and the V here. But I wouldn't be surprised if in a different year it's the other way around. It doesn't matter, whatever way it is. If it's like this, it's just the slope, but if it was the other way around, then it's 1 over the slope. So it's no big deal anyways.
EMF is mean C.
In this graph, the EMF is the C. So your battery, here,
I thought the EMF is the voltage.
yeah, the battery.
So,
So,
so it's V, right?
yeah,
Yeah.
but it's like what would be on the battery. So like this one here, the battery would say 2-volt battery, internal resistance, 1 ohm. Yeah.
So
Yeah.
in here,
Yeah.
Y equal MX plus C.
Yeah.
Y is EMF.
No, Y is the voltage in the voltmeter.
So C.
C is the intercept. It's the voltage when there's no big resistance. So like here, the V is the EMF when this is 0. Because if this resistance is gone, then the V must be the same as the E. So that's why it's this part of the graph. Then when you make this bigger, the V goes down.
To 0.
Yeah.
Then become V.
No, it becomes E up here. The V is the E when this part is 0. And yeah, but okay. So there's a current running through here. Yes, there's a current. If I make the current smaller, that means I'm moving back here on the graph. So when I make the current smaller, and then when the
Voltage.
current is zero,
The voltage.
then there's no energy lost here.
No.
So what would be on the voltmeter would be the voltage here.
Mm.
But of course you can't make it zero, because if there's zero, then these machines don't work.
Yeah.
This is like what the voltmeter would be if the current is zero. In other words, it's like what is the voltage here if none of it's going through this.
Mm.
So you can't really, I mean you could make it zero or nearly zero. So if this is nearly zero, then the voltmeter here will be the same number as the E.
Ah.
But you can't really make it zero. So what you do is you bring the graph back to here.
Yeah. Then I
Yeah.
can know
Why
if
are
this is zero.
You can know what this is.
Yeah.
why R is one?
Because you can see in my formula it's minus 1x.
Yes.
So the slope is minus 4. We get it?
Yes.
Are we sure?
Yes.
I hope so. Because I need you to make this graph for homework then. You can come in for, or this is tutorial, isn't it?
The September.
September's, not these guys. Oh good. We're having a great time, aren't we?
Yeah. Thank you.
Patrick said he's at GNIB. Yes.
Every day.
Every day, yes. It's not GNIB, it's the bank.
Yes. So busy.
Ah,
So busy.
very busy, yes.
See you later. Bye.
Alright.
Bye bye.
See you.